turbocharging, what it does is it increases the mass of air, and hence the mass of air and fuel, because for a spark ignition engine you pull in air and fuel. In a diesel you squirt in the fuel, but if there's more air you can squirt in more diesel fuel. And so it increases mass of air and fuel entering the system. And thus increasing energy input. So we're increasing the energy input, and essentially if Q dot N increases, then W dot net will increase also. So it's that simple. If I put more heat in. And what happens in a larger engine, and I'll draw a PV diagram over here so I'm not bending down. All right, I did better at that. Let me reduce this a little. Okay, so here's our actual, this is unturbocharged. And now what happens when I turbocharge it, what's going to happen is that it will fatten the curve. So basically with turbocharging, I'm going to be able to extend this curve. I'm going to sort of go out here like that. So what's going to happen is I'm going to be able to, because I have more fuel, it's going to have a more sustained energy conversion. It's going to have pushed this curve out a little bit. And for people who are changing their cars and stuff, this results in more heat. It creates more power because we can see that the indicated power goes up. But it also means, so indicated work goes up. And so the heat, there's also greater heat transfer from cylinder walls. Because I have a hotter temperature longer, so there's more heat going to the cylinder walls. So I may need to think about the radiator sizing. So this has implications for radiator. It has implications for exhaust valves. Because the exhaust valves are going to have a hotter exhaust going through them. So I have to think about the metal of the exhaust valves and whether they can withstand this higher temperature. And I'm going to have greater pressure on bearings. So when I look at it, I'm going to have greater pressure on the bearings in the piston itself. So when I have my piston, I'm going to have greater pressure on these bearings, and I'm going to have greater pressure on the bearings down here. So I'm going to have, so those are practical things that one has to take account of. And so what essentially happens in this is that we're assuming that the air-fuel ratio stays the same. We're increasing the mass of air and the mass of fuel, but their ratio, their proportion with each other stays the same. And so then the mass flow rate of the fuel is RFA times the mass flow rate of the air. And if I'm increasing the mass flow rate of the air, the mass flow rate of fuel increases, and then that m dot h sub rp increases, and we have that going on. So now let's look at how to model this with an air standard Otto cycle. Model turbocharging with air standard Otto. So sometimes for the senior design projects, people are interested in turbocharging their car, an aspirational car, their parents' car, some cars, so they're interested in that. And so for an actual engine, you're going to look up and find, so you're going to need to know the engine size, so V sub PB, the displacement, the compression ratio, R, we're going to have the RPM, and RFA. The manufacturers don't want to give you this information. So this piece of information is hard to come by. And so you'll have to look up independent dynamometer tests that people may have done to find out what this is. So this is the hard number, but this is the number that we need to calculate for the heat in, etc. And I'm going to have the power as well. W.3. So I'll have all that stuff for the actual engine that you have to get. And now we're going to do the Otto cycle design. So for the Otto cycle, and so we know how to go around this. This is where Qin is. And Qin is RFA H sub RQ. So that's why finding the RFA is a big deal in terms of this. The other stuff is fairly easy to get. So Qin is equal to per cycle. So this is per revolution. Is equal to M1 times Qn, and W net is equal to M1 times W net. M1 initial is equal to P1 V1 over RT1. M1 turbo is equal to P turbo V1 RT1. So what's happening is that what the turbocharger does is increase the pressure. So you'll look, they'll talk about boost and whatever it is. So whatever it is, I have to translate that into PSI or KPA, but probably PSI, that's what you're given. And so now I have this information all hinging on this RFA value. So notice that the Qin is going to change. The mass changes, the mass initial changes depending on whether it's turbocharged or regularly aspirated engine. And now what we're doing is we're going to say W dot break is equal to some factor. You can use your initial times W dot CO. And you get this is your air standard. So that's from your initial data. So from your initial data, you can figure out your air standard power. So basically, some factor, let's say this is 0.6. So I figured out if I know this is 60 horsepower, and I know this is 100, then this has to be 0.6. And now we're going to assume, so you're going to solve for F. Now, find W dot Theo turbo. So now you're going to find W dot Theo turbo, and we're going to say W dot brake turbo is equal to F times W dot Theo turbo. And it works. So we could use a different system. We could use the open Otto cycle analysis that we looked at. So we could do that as the theoretical one. And it gives a better approximation of the temperatures in the cycle. But in the overall, I can do it very simply. And part of why this works, if we go back to the very beginning of the chapter, we looked at the thermal efficiency versus R, and we had here a value for K. So we had whatever K is 1.3, 1.4, and then we had the actual engine. So what we're assuming is that the performance of the actual and the Otto are similar. And so what we're doing here is we're saying, all right, I will calculate this factor, and then that will enable me to do the predictive analysis with the air standard cycle to determine what I expect the output will be for the actual. And so you'll find this, you may find this handy depending on what your senior project is.